Last class, we considered energy, in the work energy theorem, we considered that work was caused by a force being applied over a distance, and that caused a change in energy. We're going to have a similar consideration today. We're going to consider a quantity called impulse. Impulse is caused by applying a force for a time, and that causes a change in momentum. Yes, that's a J. Wow. Got 1 minute into my lecture before someone started talking crap about my handwriting. Um, Unlike with the work energy theorem, these quantities are actually vectors, as we will see in our practice. I'd like to take a moment to justify this equation, though. And just like everything we've done so far, really, it comes down to Newton's second law. So F equals ma. From our definition of acceleration, we know that acceleration is a change in velocity over time. So we can go ahead and put that in. And then we play a sneaky game. Since mass is constant, right, we can bring that, inside the little delta operator. So we can consider this as the change in mv over time. And then lastly, we multiply both sides by delta t, and we get F times delta t. All of these should have hats, by the way. Is equal to the change in mass times velocity. Now that we're here, it's just a matter of definition. And the thing on the left-hand side, we just call that impulse. And on the right-hand side, we call this mass times velocity, we call that momentum. Conceptually, momentum is a lot simpler than energy, although we apply it in the same way, right? We draw a picture of our situation, before and after. And then we write down, well, external forces times time equals change in momentum. The number one situation that we are going to use this to describe are situations known as collisions, right? Something where two objects ram together with some velocity, they bounce apart with some other velocity. And that's the number one thing that we're going to use to describe with momentum. The reason why that's so convenient is because in a collision, the forces that dominate are going to be contact forces. Sure, there's gravity, there's weight, right? But in the context of a collision, the contact forces are going to dwarf everything else that the objects are experiencing. The other thing that's true about collisions is that they are short. So contact forces, if we define our system cleverly, contact forces are not external, right? The classic example here is if we have a collision between two cars, and yes, that is exactly what cars look like. When they collide, if we consider our system as both cars together, the contact forces, due to Newton's third law, are going to cancel out. So we will have forces of the first car on the second and forces of the second car on the first. Because of Newton's third law, those are going to be equal and opposite. So when we go to add up the forces, those contact forces disappear. So we have this combination of small or none external forces and small time, and those put together let us say that actually the change in momentum is exactly zero for collisions. In a universal sense, so here we'll say delta P, because of short time, small external forces. In a universal sense, just like with energy, momentum is exactly conserved all the time. Right? Last week we considered something we called non-conservative forces, forces that took energy out of our system, but they didn't destroy that energy. They just moved it into a form that we didn't want to keep track of. Right? The universe is just too big, so we have to decide what it is that we're looking at any given point. So that energy didn't go away. It just, became someone else's problem. Momentum is the same way, right? So we're going to say that momentum is conserved for collisions because it's almost exactly true, the way that we're going to define them. But in a universal sense, it is 100% exactly true that momentum is conserved. So any change in momentum in one object is going to cause an equal and opposite change in momentum in another object, no matter how those two objects interact, whether it be through gravitation, through contact forces, through electrical forces, magnetic forces, etc., etc.
May I ask a question?
Yeah, your volume's a little low, though.
Can you hear me better now?
Yes.
So when you say conservative, you mean conserved or whatever, you mean universally. You mean when we look at the whole picture. So if we were to dissect just one of the cars during a collision, then it's just going to be a loss of momentum rather than loss and gain, right? But when we look at the whole system, that's when it equals.
That is
Okay,
correct, yes.
thank you.
And in fact, most of the situations that we're going to consider won't even be like negligible external forces. They will be exactly zero external forces. In which case, our change in momentum approximately zero becomes exactly zero. So that's if we consider, that if we draw our system big enough, change in momentum will be zero. It is also sometimes useful to look at single objects, and actually, we're going to start doing problems right away, basically, because what I've put on this page, this is all the concepts from chapter 7, basically. With the exception of this is almost all of the physics from chapter 7. Yeah, we're going to talk about elastic and inelastic in a minute. Um, but since we already know about energy, that's not really a new thing. It's just a definition. Let's do some problems. Let's say that you have to slam on your brakes at a stoplight. Right? You thought you were going to make it through the intersection, and then suddenly you didn't. So now you have to slam on your brakes. You are inside your car, and you are protected by a seatbelt. What I would like to know, so if it took you, let's say it took you 1.5 seconds to start from a speed of 30 miles per hour and end up at a speed of 0 miles per hour. What is the force of your seatbelt on you? So our initial situation, which we can call situation A, our velocity is about 15 meters per second. Our final situation, velocity is 0. Now, we could use kinematics and forces to solve this problem. Just like for energy last week, we could use kinematics and forces to solve some of those problems, the simple ones. But we're going to use our new friend, impulse momentum. Let's define to the right as the positive direction. And we're going to say that an impulse is caused by a force applied over a time, and that causes a change in momentum. So, force times time is going to equal change in momentum, which is going to be momentum at B minus momentum at A. At B, we have 0 momentum because we are stopped. At A, we have momentum equal to, so we're traveling 15 meters per second. And I don't know what any of your individual masses are. I'm just going to put a mass of 80 kilograms in here. It's like an average adult person, right? So the amount of impulse we must have experienced is equal to minus 80 times 15, which is 120. No, 1,000, 1,200. We're after the force, though. So our force is going to equal, right, 1,200 over 1.5. And that's going to be 800 newtons, right? Bearing in mind a newton is a kilogram meter per second squared. Casey asks, why is the velocity 15 if we wrote v naught equals 30? Yes, so I wrote 30 miles per hour because that's typical. It's a typical speed you might be driving. Maybe you're speeding in a 25 mile an hour zone. But when you convert it to meters per second, right, there's approximately 2 miles per hour to 1 meter per second. Again, I'm rounding, generously. I am indeed recording. And I think I've even identified what causes the recordings to break. It's breakout sessions. When I enable the breakout sessions, the recording breaks. So I can be more mindful of that. Okay, any questions or comments on this example here? You're right, should be a negative sign. Right, the negative sign for momentum, it just indicates direction, right? So to the right is the positive direction. So to slow us down, our seatbelt must have exerted a force to the left. Is that another advantage of using momentum over energy? You get the direction. It can be. So that's a really good point. So in some senses, momentum is less flexible than energy analysis because there's only one kind of momentum, but there's lots of different kinds of energy you could consider. On the plus side, you do get directional information out of it, which means when we start considering two-dimensional movements, we can actually use our old trick of writing it down in the x direction and the y direction, getting two equations, and being able to solve for two unknowns. Yeah, you didn't think vectors were gone, did you? Vectors are here to stay forever. And they'll be in 152 as well. All right. Let's look at another case. Let's say we are playing marbles or something. For some reason, we're rolling balls. By the way, did anyone else start watching marble races on YouTube when sports were just gone for a few months during the pandemic? Am I the only weirdo who did that? Twitch marble streams were top tier. You are absolutely right, Kyle. Okay. So we have two marbles, and we'll say that their masses are the same, right? In the before picture, we have marble 1 is moving. And we'll say it's moving to the right with a speed of like 5. Again, we're going to be saying that to the right is the positive direction. Notice that as of yet, we have not pulled out a two-dimensional problem, but we will very shortly. The green marble we will call marble 2. It has mass 2, and its speed before these two collide is 0. All right. That's our before picture. You notice we're starting to get a little subscript happy here, right? So now our subscripts need to tell us not only which object we're talking about, but whether it's before or after. And so my personal convention is that numbers in the subscripts refer to objects and capital letters refer to situations. So V1A is the speed of object 1 at time A. B, situation B, happens just after the collision, right? So A and B are very close to each other in time, right? They are just before and just after the collision. And that's the conceit that we're going to use pretty much throughout this chapter. After the collision, both marbles are moving away from each other. Right, and the first marble is moving to the left with a speed of -2. The second marble is moving with an unknown speed. Okay. So this is what passes for a diagram in the momentum chapter. Yusuf makes a guess that it's going to be 3 for V2B, right? Presumably because this 5 gets split up into a 2 and a 3. We will see if that is correct momentarily. All right, we're still doing a one-dimensional case, so we don't have any vectors to decompose yet, so we can jump into the physics. An impulse is provided by a force acting over a time, and that causes a change in momentum. In this case, there are no external forces. There are only the contact force. So our change in momentum is 0. Right? This is if we define our system as both marbles. So if both marbles are our system, contact forces cancel out, and there's not really any other forces to consider. So the two marble system put together does not experience a change in momentum. Individual marbles do, but the two marble system has the same momentum at A as it does at B. So that lets us say the momentum at A equals the momentum at B. So the momentum of the system at A is mass of object 1, speed of object 1, plus mass of object 2, speed of object 2, and at situation B, same thing, mass of object 1 speed of object, 1 mass of object, 2 speed of object, 2. So when we go to write down, so this is very similar to how we handled energy. When we go to write down the momentum at a situation, we write down the individual momentums for every object in the system at that time. Savannah says, I don't really get that. Can you be more specific? I missed the bit that you missed. Yeah. So, right. So this is this sort of thinking is very similar to when we were doing like Newton's third law problems a few weeks ago, right? So remember we had this situation where we had a train that had like a bunch of cars behind it, and depending on how many cars we said were in our system, right, the tension between our system and all the cars after that was an external force. We're playing exactly the same game here. If we consider our system to be just marble 1, then the contact force from marble 2 to marble 1 is an external force, and marble 1's momentum is changed. Unfortunately, it's usually really hard to measure a contact force because it happens so fast. So instead of saying that our system is just marble 1, we say, well, actually, our system is both marbles. And we have no hope of being able to measure the contact forces, but we can measure the velocities before and after. That's something we can do. Okay.
I have a question real quick before we move on.
Yeah.
So the different colors, that's still the same ball, as in like under A, that's still A not colliding with B, right? I'm just a little confused with the picture.
Right. So A and B are 2 points in time. So we have 2 marbles, right? Okay. Did
Makes
that?
sense, because I thought that we're considering two different marbles. Marble A, which collided, and marble B, which collided with another marble. But now I get it. So this is two different times rather
Right.
than okay,
Yeah.
thank you.
So time A is right before the 2 marbles collide, and time B is right after they collide. All right. So we know everything in this situation except for the speed of marble B after the collision. Sorry, the speed of marble 2 at time B after the collision. Since since marble 1 and marble 2 have the same mass, actually all these masses cancel. Right? And we're able to say V1A plus V2A, that's what was left on our left-hand side over here, and we subtract off this V1B, that equals V2B. So the velocity of marble 1 before the collision was 5. The velocity of marble 2 before the collision was 0. The velocity of marble 1 after the collision is negative 2. So actually, the velocity of marble 2 after the collision has to be 7. Right? Because with momentum, unlike with energy, direction matters. So a velocity to the left is in fact a negative momentum in this case. Questions or comments? Oh, M1 and M2 are equal just because I said so. Right? Because I pulled two marbles from my collection and they have the same mass. Oh, okay. So, bunch of questions. Let me try to get to them in order. V2b is velocity after collision. Yes, V2b is the velocity of marble 2 after the collision. Um, how did you get negative 2 again? So again, that's a number I just pulled out of thin air when I was writing down the problem. I just said that the velocity of marble 1 after the collision was negative 2. Um, and then, yeah, V2b is what we were looking for in this problem. It's the only thing we didn't know.
Okay, I have a quick question. Would the answer be different if M1 and M2 were not equal?
Yeah, for sure. If they were not equal, then we just wouldn't cancel out those m's. So we would end up having M1 V1A plus M2 V2A minus M1 V1B all over M2 equals V1B. Exactly the same procedure, we would just have an M attached to everything because we couldn't cancel it out.
Okay.
Okay. Next situation. So it may have occurred to you that it's really hard to apply a force for a time if you're not also applying a force for a distance. And perhaps energy and momentum are connected in a deeper way than just using one tool at a time. And you would be correct. It is really hard to apply a force for a time without also applying it over a distance. Oh, sorry, Alexa. Let me. Okay. So we're going to consider two limiting cases here. Uh, we're going to consider two kinds of collisions, elastic and inelastic. For elastic collisions, basically imagine two rubber balls colliding, right? So you have, or maybe, yeah, so two rubber balls. This is before their collision. And then during their collision, they kind of deform because they're made of rubber. And then after their collision, they spring back into shape and bounce off. So that's the idea we have for an elastic collision. The collision temporarily deforms an object, right? So in this case, we have, the energy is all stored in kinetic energy. Yusuf, man, that's exactly where I was going. So if they deform perfectly, as rubber objects are wont to do, then they are going to store the energy that they had as kinetic energy. They're going to store it as spring or elastic energy. The details are a little more complicated than that because it's a volume deformation. So, but the idea is the same, right? They deform, and when you squish an object, it can store energy as elastic energy. And when they spring, and then after they are done colliding and they spring back apart, and if a collision is perfectly elastic, energy is conserved through all these three, right? So for an elastic collision, we have not just conservation of momentum, we also have conservation of energy. Second kind of collision we're going to consider we call inelastic. Right? So in this picture, we have we have objects coming toward each other. Poston, you are reading my mind. Man, get out of my head. That's exactly right. So imagine that instead of rubber, these were like wet clay or something. So they come to they head toward each other. They collide. They collide and deform. And when they spring apart, not everything goes back to normal. They are now permanently deformed because of the collision. So in this case, they start off with some kinetic energy. They store it as elastic energy, but not all of that elastic energy gets released. And in fact, some of this energy goes in toward basically just breaking it. All right, again, a lot of questions. Let me get to these in order. Momentum is actually unaffected by whether the collision is elastic or inelastic. So in both of these cases, we still have conservation of momentum all the time. But now the kinds of energy that we're, at least for the kinds of energy we're tracking, we do not have conservation of energy. Like when you crash into another car and get a dent, that's exactly right. So modern cars are designed with what are called crumple zones. So they are areas of your vehicle that are designed to break if you get into a collision. And the reason why this is a great idea is because if some of the energy of the collision goes into breaking your car, that's less energy that can go into shaking your body. Your car can always get repaired, but if that energy goes into your body, it could kill you. If it's clay, wouldn't it just stick together? Yeah. So it could just stick together. That's definitely a possibility. And in fact, I don't remember if this text says it, but some texts will make a distinction for a perfectly inelastic collision, in which case the two objects stick together afterwards and they move with the same velocity. So momentum is always conserved no matter what. That is correct. Why is energy not conserved here? Again, in a universal sense, it is. But we're only good at this level. We're only good at tracking like kinetic energy, gravitational potential energy, and the energy has moved into a form that we aren't good at tracking. So we say it's not conserved only because we're not tracking the kind of energy that it converted into. Oh, later you said exactly that. Yep. Inelastic happens when there are non-conservative forces. Ooh. Not necessarily. Right? So inelastic happens when you have permanent deformation. It's what we call plastic deformation actually. So if you deform an object and it can spring back afterward when you release the pressure, that's an elastic deformation. And as long as you're not squeezing an object too hard or deforming it too much, almost everything will behave elastically under small amounts of deformation. But all materials also have a point called the yield strength, where if you push harder than the yield strength, you will get not an elastic deformation that springs back, but a plastic deformation that is permanent. And so that's what's really going on here. So you get inelastic collisions when things collide hard enough to permanently deform the objects rather than just temporarily elastically deform them. Did I get to everybody's question? There was a lot in the chat, so if I missed something, I apologize.
I just want a little clarification with energy. I'm a little confused because the first and the second, we had kinetic that moved to spring potential and then kinetic again. So why is it that there it's conserved and there it's not?
That's a good question. So it's true that we have the same forms of energy. But the kinetic energy afterward is not equal to the amount of kinetic energy that went into it. So the objects are going to be slower in total.
Thank you. That makes sense.
Okay. You're welcome. Okay, so for our purposes at this level, we're going to say that collisions are either elastic, perfectly elastic, in which case we have energy conservation. They are inelastic, in which case we don't consider energy. Or they are perfectly inelastic, and this is the situation when they stick together. Right? So in a perfectly inelastic collision, they will stick together and after the collision they will have the same velocity. So v1b equals v2b. As always, the real world is a little more complicated. So there are engineers who spend their entire career calculating what is called the coefficient of restitution. And that is just the percent of kinetic energy conserved. Right, so this is a material-on-material property, very similar to the coefficient of friction. So if you have a collision, if you have, for friction, right, if you have wood sliding on concrete, you've got a typical coefficient of friction and you can do friction calculations. A slightly more complicated thing is the coefficient of restitution of, say, wood on concrete, so that if you have a collision between a wood object and a concrete object at certain speeds, then you know approximately what percent of kinetic energy the objects will have after the collision as opposed to before. You don't have to worry about that for this class. It's just a thing that exists, and I wanted to share it. Okay. One more situation that we're going to consider here. Let's say we have billiard balls. Billiard balls are hard and do not deform under contact. Which means that they have elastic collisions. You also may know, if anyone here played billiards?
Yes, they have elastic, but I thought that when they come together, they temporarily deform.
They do. Temporarily being the key word. So they spring back to their original shape after the collision. So you're taking a shot. This ball on the left is your cue ball, and you're trying to strike this second ball on its side because you want this second ball to spin off down, right? This is a pretty common shot in billiards, right? Trying to hit a ball off center.
Sorry, I'm a little stuck. Why is this not inelastic versus elastic?
So elastic is for objects that do spring back to their original shape after the collision. And if they do spring back to exactly their original shape, they get back all of that kinetic energy.
Okay. So even if we don't see it deform, it's technically, if it's the same shape, it's elastic.
Yes. Okay. So they do have a small deformation during the collision, right? Because they're made of mainly polyurethane these days. Originally, historical fact, originally pool balls were made out of ivory. All right. Where was I? Oh, yes. So we'll call this ball 1 and ball 2. The velocity of ball 1 before the collision, here this is before the collision, is equal to, let's say, 5 meters a second. But actually, if we're playing pool, we're now on a two-dimensional surface. So the time you all have been waiting for is here. So the momentum of this, or the velocity of this ball before the collision, is 5 meters a second in the x direction, 0 in the y direction. The velocity of ball 2 before the collision is nothing. We also need to consider after the collision. So after the collision, ball 1, your cue ball, goes off this way. And we'll say that it goes off at, say, a 30-degree angle. Ball 2 goes off at some angle at some speed. So the velocity of ball 1 after the collision is equal to v1b. Oh, I'm running. I need to make a little space. The velocity of ball 2 we know even less about. But we do know it's going in the down direction, which is good because we want to hit the corner pocket, which is down here somewhere. Subscript A is before the collision, the initial, yep, and subscript B is after the collision or final. That is correct. There's situations where the x component isn't cosine theta? Yeah, definitely. We just so happen to be using a coordinate system here. Well, pretend I could draw straight lines. Right? We don't have to define our coordinate system like that. We just did here because it's convenient, because that means that v1a is all in the x direction. V2b will never be negative. It could definitely be negative. Yep, my screen stopped sharing because it's group quiz time. Let me bring this back up. So choose some breakout sessions. What I would like from everyone here, I would like for you to write down the statement of conservation of momentum in the x and y directions, just like we did on the last problem. Right? So since there is conservation of momentum between A and B, I want to see, momentum at A equals momentum at B in the x and y directions, given, as much specificity as we can.